So what we'll do is we'll just start this out. I know it might have seemed like wasting time to do that, but I wanted you to kind of have a perspective for what Millikan was doing. Okay? And it was like he was solving a riddle, just kind of like you guys did. So what he did, he performed an experiment from which he was able to determine the elementary charge of an electron, okay? So as Lisa pointed out, Coulomb discovered charges and said, okay, this is a charge, but Millikan said this is the quantity of one elementary charge, and he coined that term. So recall a negative charge is due to an excess of electrons, and a positive charge is due to the shortage of electrons. So what he did is, in his experiment, he blew oil drops between horizontal plates. So in your diagram here, here's your parallel plates. He blew oil in this space, and then the oil drops dripped through. And then he was able to calculate the charge. So this is very important. We're going to be doing very similar things to what you had just learned in parallel plates. But now, since we're dealing with oil drops, they're heavy, right? Like if you just put a drop of oil, it would actually fall to the ground because the force of gravity is exerted on it so much that it would fall. Whereas our other examples, we were just dealing with like electrons and protons and stuff, and they're so tiny, their mass is negligible. So here, we need to consider gravity. Now here, when no voltage is applied between the parallel plates, the oil drops would fall to the bottom due to the force of gravity. So, force of gravity is now considerable because an oil drop is not an atomic particle and the mass of the oil drop is significant. Okay, I know this isn't a written thing, but it is significant. So, that means when you're finding F net, okay, the force exerted, you need to look at Fe, the electrical force, plus Fg, right? Fg, depending on, and we'll go through this in our examples, depending on which way the oil drop is going and which way is down, Fg might be negative and Fe might be negative, okay? But we'll work through that together. Now, when a voltage is supplied to the plate, some of the oil particles would rise to the top. Some would remain suspended, and some particles would fall faster or slower. All of these situations can be explained by the gravitational and electrical forces acting on the oil drop. So it can depend on what charge the oil drops are. They're not all going to be the same. And how heavy each of the oil drops are. Okay, because they won't come out as like perfect, all the same oil drops. Just like our film canisters had different amounts of kernels in them. Different oil drops will have different masses and different charges. So when we are solving these Millikan type problems, and Millikan type means oil drop. Okay, so when you see an oil drop kind of worded question, always start with a free body diagram and an F net equation. When the oil drop is suspended, this is so important. Suspended or moving at a constant speed, there's no acceleration. So when we look at that, if we have our F net is equal to Fe plus Fg, F net then is 0 because F net is m times acceleration. If acceleration is 0, F net is 0. So then Fe is equal to Fg. Only for these circumstances. Okay? Super important to remember that.
Would it be negative? Or does it not?
It actually depends on if Fe is going up or down. So we would get to, like, depending on the question, that you would put in negative or positive, yeah. Because they could be both going down, right? Yeah. So, and I'll show you lots of things like that. So, let's do this one free body diagram. So say I have a particle that's positive, okay? And your examples will tell you, whether it's positive or negative. Okay, so now draw in the electrical field strength. It's going out from the positive, okay, but that doesn't mean the direction the particle is going necessarily. So a free body diagram means drawing your vector arrows of forces that are acting on it. So we have Fg acting on this object. It is going down. And we have Fe pulling it up because since it's positive, it's going to be attracted to the negative plate. So now, for this situation in particular, we say Fnet is equal to Fe plus negative Fg. Because since Fg is going down and Fe is going up, we can set those to negative and positive. So now say if this is going at a constant speed, let's say it told us it's at constant speed, then our Fnet is 0. So our Fe is equal to Fg. If I take, because if I leave this here, it's positive, I take this to the other side, so it becomes positive too. So now what you can use, if Fe is equal to your electrical field strength times Q, and Fg is equal to m times G, you can rearrange to solve for different things here. So if this question asked you to find charge, you would rearrange to solve for Q. You could rearrange, you know what I'm saying? So depending on information the question gives you, but this is kind of how you approach it. You draw your free body diagram, you write out your Fnet equation, and then you kind of work with whatever it's given you and what you're looking to find.
So Fg always negative?
Well, yeah, Fg will always be going down, but Fnet, like, so say for example, my particle is negative. Well, Fg will be going down, but so will Fe, right? Fg and Fe will both be going down, so they're both negative. So it just depends on the type of question. So